I know some people aren't into green bean casseroles, but I like them. Plus, they remind me of vector fields. I mean, each green bean is like a little arrow, and I just have the urge to line them all up so they flow in the same direction. Maybe a little wavy, representing the vectors of flow in a river or something. Maybe complete with little eddies. Or maybe the beans could represent wind vectors. Long beans would be high magnitude vectors, saying there's a strong wind in that direction, and short, low magnitude beans would mean low wind speed. You could have a hurricane in your casserole dish, with the long beams of high wind speed flowing counterclockwise near the center, mellowing out towards the outer edges of the storm. The center would have the shortest beans of all, showing the calm eye of the storm. Oh, and if you're wondering why I'm not curving the beans like this, it's because while vector fields might have a shape or flow to them, the vectors themselves don't. They're usually shown as straight lines, or numbers, or both. But that's not because they are straight lines. Vectors just represent what's happening at a single point. It's like this tiny point, and this bit of wind can only travel in one direction at a time, so the bean points in that direction. And that tiny bit of wind has a certain speed, which is represented by the length of the bean, but the bean itself is just notation. Vectors themselves don't have a shape, just a direction and a magnitude. Which means a bean with a direction and magnitude is just as legitimate a vector as an arrow plotted on a graph, or as a set of two numbers, or as one complex number, or as an orange slice cut with a certain angle and thickness, or as shouting a compass direction at a precise decibel level. North. I'll admit, I'm not a huge fan of individual vectors sitting by themselves without meaning or context. One string bean does not make a casserole, or matherole, as the case may be. But fields of vectors are awesome. They do have curves and patterns, context, and real-world meaning. There are vectorizable fields permeating this casserole dish right now. The gravitational field, for instance. Gravitational forces are affecting all of my string beans, pulling them down towards the Earth. And so you could use the string beans to create a vector field casserole that actually represents the gravitational field they are currently in. Of course, this means just lining up the beans so they all point down. And since they're all affected by basically the same amount of gravity, they should all be the same length. If you are cooking at a high altitude, be sure to cut your string beans shorter by a negligible amount. Another favorite vectorizable field of mine is also currently permeating these string beans, the electromagnetic field. And if I had a giant bar magnet as a coaster trivet thing, maybe I'd want my casserole to show the magnetic field that is actually there. The points near the poles of the magnet would have larger vectors, and they'd curve around just like iron filings do when you put them in a magnetic field. And the beans would show how the force weakens as it gets further from the magnet and goes from north to south. Or if you want to be true to life and don't have a magnet, you could put equal-sized string beans all pointing the same way, and then make sure your casserole is always pointing north, which might make it difficult to pass around the table, but I think dish-passing simplicity can be sacrificed for the sake of science. Or mathematics, whatever this is. Speaking of which, you can also invent your own vector field by making up a rule for what the vector will be at each point. Like, if you just said for any point you choose, you'll take the coordinates x, y, and give that point a vector that's y, x, so that this point, 0, 5, has the vector 5, 0. And at -3, -1, you have -1, -3, and -4, 4 gets 4, -4. It's so simple, but you get this awesome vector field where the vectors kind of whoosh in from the corners and crash and whoosh out. Anyway, there's lots of other stuff you could do, but I'm gonna go ahead and pour some goopy stuff into here and get this thing casseroling. It may not look very inspiring yet, but it's far from done. The most essential part of a matherole is an awesome oniony topping, and I've got just the trick. I will even show it to you in the next video.
10-5. Okay? And I'm going to bring that up now. And if you'll take just a moment and grade your papers. So number 1 was 1/3. Number 2 is 3. Number 3 is 1/4. Number 4, it said go to the nearest 10,000th, so that's 4 decimal places. 0.7612. Number 5 is 1.079, and 6 is 0.9143. Which one?
This is
7.5. 7.5. Well, today we begin part 2. You're checking the first page. Okay? All right, so I want to talk for a minute, a quick review about places, because I had several students confused about how many decimal places is rounding to the nearest 10,000th. So I found a chart, and I've got one that hangs up in my room. I just haven't put it up yet. But if you notice this chart, here's your decimal in the middle, and then the whole numbers run that way, and decimal portions run this way. So if I had 3,000, it means I'm going to put 3 in my thousandths position. What if I had 3,541? 3,541. That means I have 1 ones, I have 4 tens, that makes 40, 5 hundredths, which makes 500, and 3,000 makes 3,000. So after you get to the decimal point and you move towards the right, you're talking about partial numbers. So their places are slightly different. The first decimal place to the right is our tenths. So let me do 1, 2, 3, 4, 5. Okay? So I've got 1/10 and 2 in the hundredths position, 3 in the thousandths position, 4 in the 10,000ths position, and 5 in the 100,000ths position. Let's think about these for a second. Tenths, that's like 1 0. 10. Hundredths is 1 0 0. Thousand is 1 with 3 zeros. 10,000 is 1 with 4 zeros. 100,000 has 5 zeros, and the millionths has 6 zeros. Look at the number of zeros we have. Oh, that's the 10th. We have 1 0. Right, in this place, we have 1 0. In this one, we have 2 zeros. Oh, that's the second place. The thousandths, that's 3 zeros. Oh, 1, 2, 3. There's my thousandths. The next one, in my 10,000ths, that's 4 zeros. So you've got 1, 2, 3, 4. That's how I remember, and that's how I learned it. Okay? So, however they ask you, if they ask you to round to the hundredth, how many zeros is that? 2. Oh, that's 2 decimal places. If they're asking you to round to the nearest 10,000th, that's 3, 4 zeros. So that's 4 decimal places. Everybody see me there? Meet me in the middle, right? So what we do is we look. I had, let me just make up a random number. 2, 3, 7, 4, 9. Okay, if they ask us to round to the nearest 10,000, well, we're going to write the number 10,000, and we're going to go, oh, 1, 2, 3, 4 zeros, so that's 4 decimal places. Okay, so I'm going to cut off here. But we don't just truncate and cut it off. They ask you to round, usually. So what you have to do is go one more place value than what you're going to write, and you look at it. and you say, is this 5 or higher? If it's 5 or higher, then you have to round up on your previous number and drop it, right? So we would say now once you round a number and you slightly alternate, you've got to use the squiggly equal sign. Means approximately equal to 2.2375. Okay, so that just means we rounded. So if you were to plug it back in and check for is this exact, you might have you might be slightly off by a rounding error. So just be aware of that, okay? Any questions? Quick little pre-algebra review there. Okay, so today we're going to talk about logarithmic equations, which is just an equation that has one or more logarithms that have a variable in it. So logs with variables is what we're going to focus on today. Our first one says, what is the solution of log 4x minus 3 equal 2? Well, there's 3 different ways they give us to solve this, but we're going to use the easiest and the most powerful, which is our big, beautiful brains. Okay? You can do this on a graphing calculator, but it's so much easier just to do it manually using our big, beautiful brains, right? So when we look at this, notice that at the back of your page, flip your page over to the back, where you see problems 11, 12, 13, which will work here in just a second. But above that, they gave us a table, and it says exponential and logarithmic form. So they give you the logarithmic form of log b of x equal y, and they give us the exponential form, b to the y equals x. So you can use those interchangeably, right? So let's look at our problem. You've got log of 4x minus 3 equal 2. Does that look like the logarithmic form or the exponential form? Which one is it? Log. So thumbs up if you think it's logarithmic, thumbs down if you think it's exponential. Some of you are missing thumbs. Okay, there we go. All thumbs say logarithmic form, and you're correct. So if you write that logarithmic form and you have log b of x equal y, and I'll go ahead and put the other one up here, b to the y power equal x, there's your exponential. We say it looks like this. That means that my base, b, well, it's not here, so it's understood to be 10. It's the natural base, right? So we've got log 10. They don't write that like they don't write a positive sign. It's the one that we use in everything we do. It's our common natural logarithm, 10, base 10. So we just don't write it. So our base is 10, b is 10. X is equal to 4x minus 3. All of that becomes our x. And our y is 2. So our b equals 10. So now we have log of base 10 of 4x minus 3 equal 2. Now, how can we convert that to our exponential form? Well, we're going to say, well, the b to the y power equals x. So we're going to say b, which is 10, to the y power, which is 2, so 10 to the 10 squared equals x, which is 4x minus 3. So we can say 4x minus 3 equal 10 to the second power. Everybody see that? Now, a way that I look at it, and the way I see it in my quirky little mind here, is I always think in algebraic terms. What happens to this thing as I tick it across the equal sign? What happens to a log as it crosses over? Well, it changes to a 10, and it's going to scoot that 2 up to be a power. See that? So it becomes 10 squared. That's the way that I see it. Oops, I need to All right, so the log, as he comes over, switches to a 10 and scoots that 2 up to a power. So it becomes 4x minus 3 equals 10 squared. Everybody still with me? All right, next we're going to just start solving for x. So what is 10 squared? 10 times 10 is 100. Then add 3 to each side, and you're going to get 103. So 4x equals 103. Then we're just going to divide each side by 4. And you'll get the x is equal to 25.75. That's all there is to it. So that's your answer. Any questions on that one? Okay, so I'll show you quickly on the on the graphing calculator. What you would do is one side of this equation, you look at both sides of the equal sign. So this side you're going to put in your L1. This side you're going to put at L2 and then graph them and look for the point of intersection. Okay, so you're going to, it's clear, go to y equals, excuse me, not L1, it's y1 and y2. Okay, so on y1 you're going to do log of 4x minus 3. And then enter, and then my y2 is just 2, a straight line, right, through the y-axis at 2. Then you're going to hit graph. And you'll see it graphs the curve, now it graphs the line. Well, you're going to have to expand this, zoom in on it, and scoot it over to see the point of intersection. Okay, but that point of intersection on the x-axis, that's your answer, 25.75. Okay, and that's how you would do that. Okay, but you don't have to do that for the test. You're going to do it method 1 using our big beautiful brains. Any questions? Okay, let's look at problem 11 on your paper and work the first one together. They give us log of 2x plus 4 equal 3. And they've started it for us. So remember what I told you about this log? As he crosses over here to the equal sign, it's going to change to a 10, and then it's going to push that 3 up to a power. So you're going to have 2x plus 4 equal 10 to the third power, which is 1 with 3 zeros. 1,000. Next, we're going to subtract 4 from each side. So we get 2x equal 996. Now divide each side by 2, and what's our answer? $498. You're correct. Very good. And that's all there is to it. Easy, easy peasy. Any questions? Okay, work 12 and 13 quickly. 12, they've started for you, and you've got like one more step after that. And 13's very much like this one we just did. Oh. Hold on. All right, so I see what I did here. Okay, now notice, what's the difference between 11 and 12 problems? When you look at the initial problem, what's the difference? One uses an extra character. What is it? Parentheses. So 12 was not in parentheses. And in my mind, I stuck it in parentheses. But there's no parentheses there, so you can't do that. And I'm leaving this on the recording because it's a very common error. And in fact, I just did it, right? So what we have to do, let me go back and erase all of this. Boom, 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 boom. Okay, so your first step is, because this is not in parentheses here, whoopsie, because it's not in parentheses, this 4z just goes with your log, right? So we have to get rid of this. So add 3 to each side. All right, so we're going to get log of 4z equal 5. Okay. Now we can get rid of the log. So we're going to have 4z equal 10 to the 5th power, which is 1 with 5 zeros. So 100,000. Now divide each side by 4, and you get that z is equal to 25,000. Okay? Good? And then 13. So 13, you've got log. And now they use the parentheses, so watch those parentheses, very important. All right, just the tiniest little thing, right, means so much. So now we're going to do that first, right? So this becomes 2x minus 8 equal 10 squared, which is 100. Now add 8 to each side, and we get 108. So we have 2x equal 108. Now divide each side by 2, and we get that x equals what? 54. Is everybody good on those three? All right, so now you've checked those. This is on your test. You've got a problem just like these. Okay. So you've got one just like problems 1, 2, 3. There's a problem just like 4, 5, 6. And there's a problem just like these, 11, 12, 13. And there's one more problem like 14, 15, 16. So let's wrap this up and look at our last problem. On number 6, problem 6, it goes with exercises 14, 15, 16. Using logarithmic properties to solve an equation, what is the solution of log x minus 3 plus log x equal 1? Well, if you look in the middle of your paper, there's that table again. And they give you the product property, the quotient property, and the power property. We introduced those in the last lesson of 7-4. Now we're going to use them. Which property, product, quotient, or power, does this equation look most like? It's going to look like one side of that equal sign. Which one does it look most like? This is an add. Which one has an add in it? The product property. So the product property says log mn, so m times n is equal to the log, oh yeah, keep b, the log, the base b, m plus the log base b of n. Well, it's sloppy, but go through the process. So what we have is the right side of this. We've got the add. So what we can do is put it back together and the multiply. So what it would be, this is like my m, x minus 3 is my m, and x is my n. So I've got to do log base b, and our base b is 10, which we don't write. So we're going to have log of m times n, which is x minus 3 times x. See? So we just we reversed that product property. That gave us the add part, and we put it back into the multiply part. Now, what we want to do is keep simplifying. So now we can get rid of that log, right? So what does it do? It becomes 10 to the first power over here. Now, let's distribute that x. And what we have to do is just get it down to one single x equals. So looks like we're going to have to factor this time, right? So before we do, distribute that x, so you get x squared minus 3x equal 10. Well, and then you're going to subtract 10 from each side, so you get x squared minus 3x minus 10 equals 0. Okay. Now you're going to use your magic x. What two factors of negative 10 add up to be negative 3? Well, it's going to be negative 5 and 2. When you multiply, you get negative 10, and when you add them, you get a negative 3, excuse me. It's negative 3. So our answer is going to be x minus 5 times x plus 2 equals 0. Now, what makes that true? Using your zero product property, well, what makes this one 0? When x is equal to 5. What makes this one 0? When x is negative 2. So we've got two answers, 5 and negative 2. Actually, let me delete. There it is right there. 5 or negative 2. So what we have to do is we have to plug in both of those answers back into the original equation and see if it makes a true statement or not. So when we plug in the negative 2, over here on the left, it does not. Negative 2 yields a false answer. So negative 2 is out. So now let's try 5. So when we plug in a 5 for x and solve, we get that it comes out to a true statement. So x equals 5 is our answer. Are we always going to have two answers? No. It's just this one worked out that way. Okay. Any questions on this one? Let's do number 14 together. On your sheet, they give you 14, and they say 2 log x plus log 4 equal 3. So the first thing I know I've got to fix is this guy, right? And we know that looking at your power property, that's going to go right here. So this is going to become log x squared plus log 4 equal 3. Now I've got that add sign, so I know I can combine this left side into a multiply. So it's going to be log of x squared times 4, which is 4x squared equal 3. Now I'm going to get rid of my log, and when he comes over here, it's going to turn to a 10 to the third power, which is 1 with 3 zeros, 1,000. Now divide each side by 4, and I get that x squared is equal to, well, 4 goes into 10 2 times with 2 left over. 4 goes into 20 5 times with nothing left over, and goes into 0 no times. So we have x squared equal to 50. Now, to clear my square, I've got to take the square root of each side. So I get that x equal the square root of 250, which is equal to 15.81. Anybody have any questions? Okay, at this point, I'm going to let you loose on 15 and 16. 15 is log y minus log 4 equal 2. So now we've got a minus, which means that's going to be your quotient property. You're going to use that one to solve. Okay. And then 16, you've got log 10 plus log 2x equal 3. So again, you've got that. So that's going to be the product property. So they're going to multiply 10 times 2x, which is going to be log 20x equal 3, and take it from there. Alright, so solve those in about 2 minutes. I'll take your papers up. And then just work on your study guide for your test. And then that'll be your homework tonight. We'll go over it tomorrow, and the test is on Thursday. This concludes our lesson. Thank you.